and that is the 3D structure associated with these things. Remember I talked earlier on the first slide about how the three-dimensional structure of the enzyme is ultimately what allows it to do its work, because it has specific active sites in it, and that the substrates go into those active sites. So this three-dimensional structure is going to be critical. Now you have 4 levels of structure that fold up to make the three-dimensional structure. So the first one is called the primary structure. Okay, that's a little degree sign for primary. And the primary structure, if we're just doing it schematically, is simply the linear sequence of all the amino acids. So each one of these little beads I'm showing here, and would go on sometimes for tens of thousands of amino acids in a row, all linked by black peptide bonds here, that's called the primary structure. So that's the linear sequence of bonded amino acids. Then we have the secondary structure. And there are 2 types of secondary structure that exist that you need to know. One of them is called the beta sheet. That's a B, beta sheet. And the other is called the alpha helix. And a protein can have both these things, and you'll see and understand why that's the case. So, sort of, if we were to schematicize this, hold on, Cal's calling me. He wanted to go to dinner, so we're going to have to make this fast. A beta sheet is like a folded piece of paper, okay? Kind of like an accordion. Now keep in mind, that's what it would look like on edge, but it would actually be like a sheet of paper that's been folded. So, I don't know, I could make some three-dimensionality out of this whole thing and really probably make it a mess. Oh, that's not too bad. I do this. Yeah, oh, hey, I'm good. All right, so it looked like that, except they wouldn't look like individual little teepees. This is a single folded piece of paper. So that's the beta sheet, okay? And then the alpha helix is a simpler thing. It's sort of like a spiral, okay? So once you can convert, it's hard to imagine converting this linear sequence into a beta sheet, but it connects against each other, zigzags, and holds together as a flat surface, and then it's folded. You can more easily imagine the alpha helix structure here. Looks like I need to give us another. So let me go to the last 2. We have tertiary structure, and that's when you take a whole bunch of these beta sheets and you actually fold them on top of each other. Okay, so you take that secondary structure and you fold it, or if it's the alpha helix, then this all gets folded up. Okay, so that's the tertiary structure when you fold the secondary structure. And then lastly, we have the quaternary structure. I'm going to spell that because nobody spells this right. It's Quaternary, quaternary. And quaternary structure, yeah, I can't really go, maybe I can go back. Let's see. Can I go back? No, can't go backwards. No, I did go. No, oh well. Yeah, here we go. I did go backwards. All right, so tertiary structure is also held together by hydrogen bonds, but also by something called disulfide bridges, which are sulfur connected to sulfur. So sometimes there's sulfur hanging out in these amino acids, and they happen to be hanging out opposite sides of each other, like so. And then there's a bond that forms between them that holds these tertiary structures together. And if I could go backwards, I'm not even going to try to do this because I can't. I'm terrible at using this new screencast maker. But secondary structure is also held together by hydrogen bonds and disulfide bonds. And then the primary structure is held together by, you guessed it, peptide bonds. So don't get that one mixed up. All right, that's it. I know this was a lot to absorb, but I think you're tough and you can do it. Bye. Is when you take, let's say, an alpha helix structure and you stick it next to another separate alpha helix structure, and they bond together using intermolecular bonds like hydrogen bonds to hold them together. And it could just as easily be, and so this is tertiary structure, it could easily be that you take an alpha helix and make it stick next to a beta sheet next to another alpha helix. So it really is, in this case, it's separate polypeptides that are associated with one another through hydrogen bonding. This whole blob, actually, I could make this one big protein, and it's very possible that one big protein would have several of these what are called motifs all connected to one another. Okay, so quaternary structure is the most complex level, and it is not all proteins actually do quaternary structure, but some of them do. And again, it's mostly held together by hydrogen bonds. And in fact,